Okay, so welcome back to another video. So in today's video we have the following contest problem from the 1970 IMO, the International Mathematics Olympiad, and this is question number 3. And so we're dealing here with some sequences over here. So the problem says the real numbers a sub 0, a sub 1, all the way to a sub n, and then the terms can continue so on and so forth, satisfy the following conditions. We have that 1 is equal to a sub 0, which can be less than or equal to a sub 1, less than or equal to all the way up to a sub n, and so forth. And so the numbers b1, b2, and then b sub n are defined by b sub n is equal to this partial sum all the way up to the nth partial sum of 1 minus a sub k minus 1 divided by a sub k divided by the square root of a sub k. And so we have two things that we want to show. So part A asks us to prove that 0 is less than or equal to b sub n, which is less than 2 for all n. And then the second is, given c with 0 is in between that same inequality just like above, prove that there exists numbers a sub 0, a sub 1 with the above properties such that b sub n is greater than c for some large enough n. So of course, all this is going to be doing with some using definitions of sequences, and then there's actually going to be a bit of calculus and analysis involved with this. So this is actually going to be really interesting. So let's start off by just rewriting our b sub n definition over here. So if we simplify some stuff, well, not really simplify, but we actually can expand this out just a bit. We know that b sub n can be rewritten as the partial sum. This is k is equal to 1. This can be rewritten as a sub k subtract with a sub k minus 1, and then divide this with a sub k and then multiply with the square root of a sub k, like so. You could basically just do your whole converting into put this under one denominator, and then use that fact that you can move the a sub k under the denominator from here, and then rewrite it like this formulation as so. We can keep moving forward and say that this can also be rewritten as, so a sub k and then times the square root of a sub k. You can combine the exponents together, and then that's the same thing as saying a sub k to the power 3 over 2, that's under the denominator, so that means I can just write that as the negative exponent. And so we have that this is a sub k minus a sub k minus 1, then multiply with a sub k to the power negative 3 divided by 2. So now we're actually going to construct a little picture here, so give me 1 second before I jump onto the next step. Okay, so here's our little picture described here. So the next thing we want to do is we want to define x sub k to be the rectangles with the following 4 vertices. We have that one vertices a sub k minus 1, and then the x as the x coordinate and y coordinate respectively 0, a sub k 0, a sub k, and then a sub k to the power negative 3 over 2. That's what that curve is defined as, that function. Here I'll write it like this. So we could say that f of x is, for example, in this case is, or rather, f of a sub n is equal to a sub n to the power negative 3 over 2, for example, in this function. So we have these following vertices defined over here, and then this is what the construction looks like. So we have, so of course we're given the condition that the following condition with 1 equals a sub 0, so that's where this is supposed to be 1 over here, and then listed off in each terms a sub 1, a sub 2. There constructs the construction of the rectangle here defined with these following vertices over here. Okay, so now that would mean that we can say that for all k that are the natural numbers, of course, that would have to mean that the area of these of the x sub k's, these rectangles, is such that it's defined as, so we have that a sub k minus a sub k minus 1, and then multiply with a sub k to the power negative 3 divided by 2. That's simply just equal to, well, the area is this for a rectangle, and we have to calculate, and we're having all these rectangles over here, so that means we want the sum. So we have that this is actually b sub n is equal to the partial sum of, so k is equal to 1 to n of the rectangles x sub k. All right, and then now you'll notice that for all sequences of a sub k, for all natural numbers k, of course, then you see that the rectangle actually lies above the x-axis, and it's below the curve, you can just replace the a sub n with just x in this variable. So f of x is equal to x to the power -3 over 2. And of course it's divided between, and of course we have that our bounds are between 1 to a sub n, since we have, you know, the condition with 1 is equal to a sub 0, which is where it starts here. And you just keep going all the way up to a sub n, which can actually just go on infinitely. So, and it's also worth noting that all these rectangles are disjoint. So that's one thing to keep in mind. And now with that, we can actually do the little calculation. So now we can do the calculation over here. This is good. So we have that b sub n is equal to, so we have the, you know, our partial summary over here. So it goes from k is equal to 1 to n of capital X of k. And we can define this inequality such that we can actually use the exact value. So really we can define this as the integral, since integrals is basically you're calculating the exact area underneath the curve, but since we have these partitions of the rectangles, we know that the area of those sum of those rectangles is supposed to be less than the exact value of our integral we're evaluating underneath this curve. So we can actually use that to our discretion right here, and we can define this from our bounds from a sub 0 to a sub n, where a sub 0 is equal to 1, and then a sub n, and then with our function, in this case x, and then to the power -3 divided by 2 dx. And then this is basically just simple over here. You know that you just add 1, so you get -1/2 divided by 2, so it's -2, then times x to the -1/2, which that's the same thing as -2 to the power divided by square root of x. Evaluate from your bounds of a sub n to 1, and then of course you just evaluate this. So let's see, you have -2, then divided by square root of a sub n, minus, and then minus this. So I can just move that to the front. So if you plug 1, that'll just be 1, and then that'll change to positive, so that means we have 2, and then subtract with 2 divided by the square root of a sub n. And of course, obviously you can see that 2 minus anything, any finite number, of course, that's actually going to be less than 2. So of course, with this, we have actually just proved part A, that the 0 is less than or equal to b sub n less than 2. The whole point with 0 is that we can even have that a sub 1 be equal to 0, just like right over here. So we can also have an area of 0, so this actually works with this as well. So now next is to prove part B, which given c with 0 is less than or equal to c less than 2, prove that there exist numbers a sub 0, a sub 1 with the above properties such that b sub n is greater than c for some large enough n. Let's see, so if we were to choose, by choosing a sub k equals to 1, since we have that it starts at 1 over here, the smallest we can be for that x term in this case, and if we add this with some k, and then multiply with some delta x, such that delta x is greater than 0, we just say this because, you know, the constructions of these rectangles doesn't have to be exactly like this. It can even be constructed in many ways possible. It can even be the smallest rectangle you can be. So that's why we actually just define some term for a sub k and how it's placed upon right here. So with this, you can also see from this is that, because this is also with the whole approximate, well, not really approximate, but we're getting it closer to the true value. So we can see that b sub n is actually in the form of a Riemann sum. It's actually b sub n is the Riemann sum for the integral, so given above. So a sub n and then x to the -3 divided by 2 dx. Well, okay, and so therefore, let me put it this way. Therefore, if we were to write this in the limits as we actually get closer to 0, because it's with this whole like integration that you want this to be as exact as possible. So as we're taking smaller numbers of delta x that's not equal to 0, we're actually getting closer to the value. So this means I can just write this as a limit from delta x approaching 0 plus, from coming from the right hand side of b sub n, then that's actually can be defined as the Riemann sum of above. So 1 to a sub n of x to -3 divided by 2 dx. Now with this, now we can actually take the limit for n goes to infinity. So when we do this, so this is the limit n approaches infinity of the limit delta x approaches 0 from the right to b sub n. So simply that's just equal to the limit as n approaches infinity of the our definite integral from x to the negative 3 over 2 dx. And then of course we already calculated this. That's actually just the limit as n approaches infinity of 2 minus 2 divided by the square root of a sub n. Well, simply we could just replace this k with n and just replace this back with 1 plus n delta x. So this means we have, let's see, I'll just write this, the limit as n approaches infinity of 2 minus, let me replace this with, this is 1 plus n times delta x, and then this is a 2 over here. Now, if you were to take this limit as n approaches infinity, obviously you can see that this is going to be a bigger number here. 2 divided by that, then that means this whole thing is going to go to 0, and therefore this is just going to equals 2. And so the last thing to say is that, so for any c that is in the interval from 0 inclusive, and then not including 2, then we can choose some small, delta x that's greater than 0, such that we can form this sequence a sub n satisfying these above properties, such that b sub n is greater than c for some large enough n as desired. So yeah, we just proved our two little givens right here, and with all this with the calculation above, and there's that. So yeah, that's pretty cool if you ask me.